Hello all, today we are going to see about a traveling salesman problem using branch and bound. So first we need to understand what is branch and bound. Branch and bound is an algorithm design paradigm which is generally used to solve optimization problem. So in problems which we need to find the optimized solution, best solutions, in such problem we have to use branch and bound. So compared to the backtracking which was taught earlier, it is used to solve permutation problems. In the backtracking, using backtracking, we were interested in finding the all possible solutions. For instance, in the sum of subsets, we were interested in finding all possible solution. So, but in branch and bound, we are only interested in finding the optimized solution. The other difference which can be kept in mind while comparing the backtracking and branch and bound is that in backtracking is a depth first traversal. We would do a depth first traversal, and whereas in branch and bound it is breadth first traversal. So all this would be you'll be getting clear as and when we move on with the video. So this is the problem statement. Today we are going to see that is a traveling salesman problem. So the problem statement is this. So when we are given a graph, so this is the graph we will take, so which has 4 vertices in it, and it is an undirected graph. So a salesman has to start from one vertex, and he has to visit all the vertices, and he has to return to the starting point, and he has to do it he can have more than one path. So for instance, in this graph, he can travel from 1, 2, 3, 4, 1, 2, 3, 4, and he can return to 1. Or he can choose this path 1, 4, 3, 2, 1. So he can choose this path also. He can travel back to 1. So this is not connected, but still it's there. He can have more than one path, but to do this, but he has to choose the optimized path. That means he has to choose the one which throws the least cost. So normally the edges would be labeled with cost. So I did not put it here. So we will take another example in which we will see. So that is the problem statement. So the traveling salesman, I'll repeat this problem statement once again. A salesman has to start from one starting point, and he has to visit all the vertices, and he has to return to the starting point in a minimum cost. So that is the problem statement, and we are going to deal this using branch and bound today. So this is an adjacency matrix we are going to take today to solve the traveling salesman problem. So the graph of the adjacency matrix, I'll show it later. So we know that how to understand the adjacency matrix. So these are the cost of the edges between connecting the vertices. So this has to be understood like this. The cost of the vertex, the cost of traveling from the vertex 1 to 1 is infinity. So it's always like that. And when there is no edge between two vertices also, it will be given the cost infinity. So cost of traveling from 1 to 2 is 20. The cost of traveling from 3 to 30, and so on. So this is the adjacency matrix for which we are interested in finding the minimum cost. That is a traveling salesman problem. This is the graph I was talking about, for which we saw the adjacency matrix. So he has to start from vertex 1, and he has to visit all the other vertices, and he has to return to the 1. So he has now 4 possible vertices he can travel through. He can either choose 2, 3, 4, 5. I said it's a breadth first traversal. So he has to, we will analyze in a breadth first fashion. We will analyze first 2, 3, 4, and 5. So that's what we are going to do. So first we need to understand. So before we do this, we need to understand the cost of the first starting vertex. That's what we are going to do right now. So the step 1 is that we need to find the cost of the starting vertex, that is 1. So to do this, we need to find the reduced matrix of the given adjacency matrix. So how to find the reduced matrix? So we find the reduced matrix by identifying the minimum element of each row. So when we look at the adjacency matrix, so this was the adjacency matrix given to us. So the minimum element in this row is 10, and this row is 2, and this row is 2 again, and in this row it is 3, and in this row it is 4. So let's not bother about the infinity. So here what we need to do is that row-wise reduction means we need to identify the minimum element in each row, and we have to subtract all the elements by that minimum element. So this 20 would become 10, and this 30 would become 20, and this would become 0, and this would become 1. And we have also need to do it column wise after doing it in the row wise. So remember, after reducing it row wise, we need to find the minimum column wise element and we have to subtract. That's what we are going to do now. So we've already done this. So the 10 is the minimum element that was taken from the previous adjacency matrix, and we have subtracted the element. So we need to sum this up and we get it as 21. So that means in each row, what is the minimum element, and this is summed it as 21. And now we have to find column wise also. So column wise elements, minimum elements are identified. So as 1, and here it is 0, it is 3, and we have subtracted after finding the row wise reduction, we identify the minimum element column wise and we subtract the minimum element from the row wise reduced matrix, and we have to sum all the column wise minimum elements, that is 1 plus 3. So rest of them are found to be 0. So the row wise reduction, the minimum elements is sum was 21 and the column wise minimum element is 4, and we get it as 25. So we need to understand this as, so the cost of the tour, which will at least take 25. So but the minimum cost can be more than this or less than this. So we need to explore that. Right now, the cost of the node 1, we take it as 25. So that's what we understand. So the step number 1, remember, so in step number 1, we found the reduced matrix. So the reduced matrix was constructed by finding the minimum row element, and we subtracted the row element from the given adjacency matrix. And after finding the row reduced matrix, we found the column reduced matrix, and then we took the sum of the minimum elements row wise and column wise, which is the cost of the node 1. As I said earlier, so we found the cost of the node 1, the starting point, that is 25. So we need to have a upper bound for the starting point. So initially it is infinity. We will update this upper bound after finding the leaf node of the state space tree. So we know this is a state space tree through which we are going to explore the problem. So now the second step is to find the cost of traveling from 1 to 2, 1 to 3, 1 to 4 and 1 to 5. I said this is it was said that it is a breadth first traversal. So we need to analyze the problem in a breadth first fashion. So now we need to find the cost of cost of node 2, that is traveling from 1 to 2. So that's what we are going to do now. To find the cost of node 2, we need to find the reduced matrix for 2. For finding the 2, remember we need to consider the reduced matrix we obtained from while finding the cost of node 1. So the appropriate matrix should be considered. So this we will understand as and when we move on. So to find the cost of node 2, the way to do that is that we need to make the first row elements, so we will make the first row elements and the second column elements as infinity in the reduced matrix we got from while finding the cost of node 1. Also, we are interested in finding the cost of traveling from 1 to 2 now. So 2 to 1. So the cost of traveling from 2 to 1 should also be marked as infinity. So you've done this. This is the reduced matrix we got from the node 1 cost calculation. We have made all the first row element as infinity and second column elements as infinity, and the cost of traveling from 2 to 1 is also made as infinity in the reduced matrix we obtained from step 1. So now we have to do the same way we did for cost evaluation of node 1. The minimum row element needs to be taken. So all this is infinity, so we'll take it as 0. So here it is 0. So here also it is 0. So here the minimum row element is 0. So here also it is 0. So we need not subtract anything. It's already 0. And after, so we need not subtract, so we will find the column wise minimum elements also. So they are also found to be 0. So 0 is the minimum element. Here everything is infinity, we will take it as 0. So here it is 0. So here we find a 0 here, and here it is 0. So we need not find any reduction here. So the total reduction, that is R cap, is 0. So 0 plus 0, that is 0. Alright, so now we are how to find the cost of node 2. So this is how we are supposed to find the cost of node 2. The cost of node 2 is the original cost of traveling from node 1 to 2 plus the cost of the parent node, that is node 1, plus reduced cost. Reduced cost, anything we found here, so we do not find anything, that is 0. The cost of the parent node is 25. The cost of traveling from 1 to 2 is 10. So that's what 1 to 2 is 10. So we can identify from this reduced matrix 1 to 2. The cost of traveling from 1 to 2 was 10. So 10 plus 25 plus 0, that is 35. So this is the cost of the node 2, which is given as 35. Now we need to understand the same way, and we have to evaluate the cost of 3, 4 and 5. So now we need to find the cost of node 3. So we took the reduced matrix we got from the evaluation of node 1. Remember, appropriate reduced matrix should be taken. So the parent node is 1. So the appropriate reduced matrix we got while calculating node 1 has to be taken. So this is the same way we will reduce the matrix. So to do this, what we will do, we will make the first row elements as infinity and the third columns as infinity. Also node 3 to 1, that should also be made infinity. So in the reduced matrix we got while calculating cost of node 1. Similarly, so we have to find the row wise minimum elements and we have to subtract them. So all this is infinity, so 0. So here the minimum element is infinity. So here it is 0. Here also it is 0. Here also it is 0. So we get it as 0. And column wise we can find. So here the minimum element is 11. So we have to subtract 11 from each and every column in the first column. So 11 is subtracted, so we get this one. And here it is 0, here it is infinity, so I will take it as 0. So 0 is the minimum element, 0 is 11. So the reduced cost we have it as 11. So this is the reduced matrix we obtained while finding the cost of node 3. This has to be marked. So now finding the cost of node 3 is cost of traveling from 1 to 3, that is in the reduced matrix we can find. So this is the reduced matrix of node 1. The cost of traveling from 1 to 3 was 17. So that is how we got this 17, and the parent node cost, that is node 1 cost, that is 25, and any reduction R cap we found it as 11. So 11, so the total cost of the node 3 is 53. Similarly, we need to find now the cost of 4 also. To find 4, so we have to make the first row as infinity and the fourth column elements as infinity. Also the 4 traveling from 4 to 1, that needs to be made as infinity, and we have to find the reduction, the minimum row element and the column wise row element. So remember, always find the minimum row element, subtract if there is any minimum element, and then do the column wise row reduction. So it should not be done simultaneously. First row reduction should be done, and after finding that we need to find the column wise minimum element and we have to subtract. So here also we found zeros. So the cost of node 4 is nothing but cost of 1 to 4. So we need to understand from the reduced matrix we got while calculating the node 1 cost. So 1 to 4, that is 0. So there is no cost, plus the cost of parent node, that is 25, and we did not find any reduced cost here, so that is 0. The cost of node 4 is 25. So now we are in the position to find the cost of node 5. Similarly, we will make the first row element and the fifth column elements as infinity, and we will find the reduced matrix. So here we have 5. So this is because in the second row we had 2. So we have to subtract 2, and in the fourth row we have minimum element as 3, and we reduced the cost. So the 12 became 9, and the 15 became 12. So why? Because we subtracted this minimum element. And after doing that, we found column wise element. So those were all 0. So 5 plus 0 is 5. So the cost of 5, the cost of traveling from 1 to 5, so which is which can be seen here from the reduced matrix. 1 to 5 is 1. So 1 plus the parent node cost, which is cost of node 1, that was 25, and the reduced cost we got as 5. So the total cost of node 5 is 31. Okay, so the first level is completed now. So the cost of node 2 was 35, and this is 53, and 25 and 31. So we are interested in finding the optimal solution. So obviously we will find the one which threw the least cost. That was the node 4. So we are interested in exploring the node 4 as of now, and we are not bothered about the rest of the nodes. If required, we will bother about them, but right now we will only explore node 4. Okay, so now we have to remember the appropriate matrices while traveling down. So we are now interested in finding only the reduced cost. That we from the matrix we obtained from while calculating the cost of the node 4. So earlier we were finding the cost from the matrix we got from node 1. So now we have to only bother about the matrix we obtained while calculating the cost of node 4. So these are the matrices I've given for your reference. This was the reduced matrix we got while calculating the cost of node 2, and this is the reduced matrix we got while calculating the cost of node 3, and this is the reduced matrix we got while calculating the node 4, and this is for 5. Now we have to use this matrix while we explore the rest of the path cost. Sorry for the confusions here. So now we from 4, the salesman can either choose 2, 3, 5. So which you can cross check with the graph which was shown earlier. So there are 3 possible ways he can do this. So now this is a breadth first traversal. So we will explore the cost of traveling from 4 to 2 and 4 to 3 and 4 to 5. Then we will choose the minimum cost, and then we will explore it further. So first we will explore the cost of traveling from 4 to 2. So for doing this, we will only consider the matrix which was obtained while calculating the cost. So that was said earlier. So we will find the cost of node 6. Why I have numbered this is that because we have to remember the appropriate matrices while calculating. That's why these numbers are given. These numbers are just to denote the matrices number we get while reducing each and every node. So these are the vertices number. So we'll find the cost of the matrix 6. That means the cost of traveling from 4 to 2. That is given by the cost of traveling from 4 to 2. This has to be obtained from the matrix we got from the 4. So 4 to 2 traveling is 3. So that is 3. And the cost of the parent node is 25. Cost of 4 is parent. So whose cost is 25. So 25 is added plus any reduced cost. So this reduced cost we know how to calculate. So we have to take the fourth matrix and we have to reduce it row wise. So before reducing it row wise, what we will do, since we are finding the cost from traveling 4 to 2, we will make the fourth column elements as infinity and the second column as infinity, and then we will reduce it row wise and then we will reduce it column wise. So fortunately, we got all the elements as minimum elements as 0. So we do not have any extra cost. So this 3 plus 25 plus 0 is 28. Now we have to find the cost of node 7. That is node 7 in the sense we have to calculate the cost of traveling from node 4 to 3. So we have to take the fourth matrix and we have to make the fourth row as infinity and third column as infinity, and we need to find the reduced matrix cost. So the cost of traveling from 4 to 3. So this has to be taken from the fourth matrix. The cost of traveling from 4 to 3 is 12 plus the parent node cost. The parent node cost is nothing but the parent node is node 4, remember, and that cost is 25, and the reduced cost we got it from the matrix as 13. So we know how to calculate the reduced matrix. I think I need not repeat. So the reduced matrix, we take row wise and then subtract them, and we sum the elements. We got row wise and column wise. So that seems to be 50. So the cost of the node 3, that is traveling from 4 to 3, is 50. We are done with finding the cost of 2 and 3. And now we are left with 5. So the similar way we will find. So we need to make the fourth row as infinity and the fifth column as infinity, and we need to find the same way. So the cost of traveling from 4 to 5, so which is 0. So 4 to 5 is 0. The cost is 0, and the cost of the parent node, that is 25 plus 11. So the reduced cost is we got it is 11. So because we have some 11 in the minimum while finding the minimum row wise element, so this comes to be 36. So now we have got 28, 50 and 36. So we are interested in finding the optimized solution. So we'll only bother about the node 2, which has least cost now. So we'll explore further node cost, explore this path. Remember, that is why we marked this this as 6. So we need to bother about the matrix number 6 we got while calculating the cost of this node. So that matrix needs to be focused while calculating the further cost. So from here we can either, we now have two choices with us. Either we can go to 3 and 5 to reach the source vertex. So first we will explore this path, and then we will explore this path, and we will pick up the least one. So first, this is numbered as 9. Remember, the matrix we got, we numbered as 6 has to be now taken to find the cost. So this is the matrix, and to find this, since we are interested in finding the cost of traveling from 2 to 3, we need to make the second row elements as infinity and third column elements as infinity. Also from 3 to 1 should be made as infinity. So so now this is the matrix, and the cost of the node 9. So that is 3 again. So we are interested in finding that. So here we have made second row as infinity, third column as infinity, and 3 to 1. 3 to 1 is also marked as infinity, remember. So 3 to 1 is also marked as infinity, and we reduce that column wise, so we get it as 13. So now it comes to 52. So this 2 to 3, the cost of 2 to 3, this should be taken from the matrix 6. The appropriate matrix should be referred, and then the cost of traveling from 2 to 3 plus the parent node cost, which is the cost of node 2, that was 28, and the reduced cost is 52. Again, so this is 52. In the similar way, we calculate the cost as for traveling from node 2 to 5, that is 28. So this is the lesser than this path. So obviously we will choose 5. So obviously we will choose 5. So what we have observed is that from node 1 we got this as the least cost at this level, and then we explored this node and this explored this node. So obviously there is only this path can be observed, and we have reached the leaf level. So we said earlier that when we reach the leaf level, we can update the upper bound. The upper bound was initially 28. Now we have reached the leaf level. So that is the least cost is 28. So we can update the upper bound as 28 in the root node. So now we have to see, we can check whether we need to explore the levels, the node levels at 1, which is lesser than 28. The upper bound is 28. So if anything is lesser than this upper bound, we can explore that cost, that node's cost. Otherwise, we can leave it. So greater than 28. So the rest of the nodes are throwing, the rest of the cost are greater than 28. Greater than 28. So we can kill all the nodes. I think this is 28, I'm sorry. So all the nodes are greater than 28, the upper bound. So we need not explore all the rest of the paths. So we can conclude that this path, what we have explored till now, so 1, 4, 2, 5, 1 is the optimal path we found using branch and bound algorithm for traveling salesman problem.